Okay, this one is a me problem. Um, I don't know if I'm going to do every last part of it. I think I'm going to leave point C for you to figure out. Um, but I'm going to do some of it. So two very large non-conducting plastic sheets, each 10 centimeters thick, carry uniform charge densities sigma 1, sigma 2, sigma 3, sigma 4, and sigma 4 on their surfaces as shown. These surface densities have the values given there. Use Gauss's law to find the magnitude and direction of the electric field at the following points, far from the edges of the sheets. Okay, here's the key thing. Remember, we found that electric fields from infinitely long sheets did not depend on how far away you were from the sheets, and they pointed straight away or straight away from or straight towards the sheets. Okay. If I draw a surface here, I can draw a surface that has an area A on this side, a similar area A, actually I don't want to put it there. I know that a long ways away from any of these, the actual detailed structure of what's inside here won't matter. And the field is nice and constant on both sides. So there's every reason to expect that it should be the same on both sides. Far away, I wouldn't be able to tell which side was which, and they're constant. So I'm just going to draw a cylinder like this. It doesn't have to be a circular cylinder. We do want to make sure these sides here run parallel to the electric field. And then I've got an area on the right here and an area on the left here. Okay. So what do I have to work with here? I have the integral of E dot dA is equal to the charge enclosed over epsilon naught. All right. So for that cylinder, the flux, I've got the integral over the left of E dot dA plus the integral over the right of E dot dA plus the integral over the side of E dot dA. And that's going to equal the charge enclosed. Now, as it happens, in this case, the side runs parallel to the electric field lines, which means the area vector is perpendicular to them, and this dots to 0. On the end caps, the electric field is constant, and the angle between the electric field and the area vector is 0. So this just becomes, we don't need to worry about the dot product because the angle between the area vector and the electric field is 0. There's every reason to believe this is symmetric with both either pointing outward, I should have that outward, or both pointing inward. So if they're both outward, they're both in the same direction as the area vector. If they're both inward, they're both in the opposite direction. Either way, it's the same result. This is just E left, area of the left, plus E right, area of the right. We think those are the same. So this is just 2E at point A times the area. Now let's start thinking about the charge enclosed. Notice each of these are a surface charge, and each one has the same area enclosed as the area of this cylinder. So my charge enclosed is going to be the area times sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay. So when I put this all together, I find that 2 E at point A times the area equals sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 times the area all over epsilon naught. I can cancel the areas. I can divide through by 2. And I find that the electric field at point A is just the total of all of those surface charge densities divided by 2 epsilon naught. Okay, but that one's comparatively easy. That's just the same as the problem done in the book, the same as the problem I've done in the video lectures. Very similar to what you did in the tutorial. So now let's do one that's a little more challenging. All right. Let's look at point B. Now here's the thing. I'm going to arbitrarily guess that the field at B points from left to right. Okay. And I'm going to draw another cylinder here with the left-hand side being in the same field that is at A. So now my total flux, I still have the electric field at A times the area. But on the other side, I have the electric field at B times the same area. But now, because I'm in between the plates and we don't know, we're close up and we don't know how things are going to behave, we don't know that the field in between is the same as the field on the sides. So I can't just set those equal to each other. What I can do is I can set them equal to the charge enclosed, sigma 1 plus sigma 2. All of that times the area divided by epsilon naught. Okay. Area vectors cancel. And what it comes down to is that EB is equal to sigma 1 plus sigma 2 over epsilon naught minus EA. And that actually can be simplified somewhat. Sorry. I don't know what happened to the file I was working with. Well, now I've lost all of that work, but that's okay. All right, I remember the results. EA was equal to sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 over 2 epsilon naught, and EB was equal to sigma 1 plus sigma 2 over just epsilon naught minus EA, but that is sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 all over epsilon naught. Notice, what on earth? Damn it. I don't know what happens when I lean that down. Okay, so E at B is sigma 1 plus sigma 2 all over epsilon naught minus sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 all over 2 epsilon naught. So the ones on the right are each half as much as the ones on the left. So sigma 1 over epsilon naught minus sigma 1 over 2 epsilon naught is just sigma 1 over 2 epsilon naught. Sigma 2 over epsilon naught minus sigma 2 over 2 epsilon naught is just sigma 2 over 2 epsilon naught. And then these ones here end up negative. End result, the electric field at B is equal to sigma, damn it. By the time it came back. Sigma 1 plus sigma 2 minus sigma 3 minus sigma 4 all over 2 epsilon naught. If we had done it from the other side, if I had looked at it over here, this would have been EA. If I'd assumed that this was still going to the right, this side would have gotten negative EB times A. So my total flux would have been EA times the area minus EB times the area. And that would equal sigma 3 plus sigma 4 area over epsilon naught. So in that case, EB would have been EA minus sigma 3 plus sigma 4 over epsilon naught. All right, and that, you can check it out, will give you the exact same result that we just saw, namely sigma 1 plus sigma 2 minus sigma 3 minus sigma 4 over 2 epsilon naught. To find the field at C, you're going to need a box, a cylinder, with one side at C, and the other side could be here on this side at B. It could be over here, knowing the field at A, or it could be over here, knowing the field on the right side. Okay.